Here next to me, I'd like to welcome you all to this panel on AI history devoted to the story of expert systems. I'm David C. Brock, an historian of technology and the director for the Center for Software History, thank you, at the Computer History Museum in Mountain View, which I encourage you all to visit. Today I'll be acting as your semi-autonomous agent as moderator for the coming discussion. Our panel is also so illustrious that perhaps the briefest of introductions are the most appropriate. Edward Feigenbaum is Kumagai Professor Emeritus at Stanford University and was president of this association for 1980 to 1981. Ed was awarded the Turing Prize in 1994 in part for his role in the emergence of expert systems. Bruce Buchanan is University Professor Emeritus at the University of Pittsburgh and was president of this association in 1999 to 2001. Randall Davis is a professor in the Electrical Engineering and Computer Science Department at the Massachusetts Institute of Technology and serves on the executive cabinet for its Computer Science and Artificial Intelligence Laboratory. He was president of this association for 1995 to 1997. And Eric Horvitz is a technical fellow of the Microsoft Corporation, where he also serves as the managing director of Microsoft Research. He was president of this association in 2007 to 2009. So to begin, why open a discussion on the history of expert systems now? As the abstract for this session notes, everyone here is quite aware of the current enthusiasm for recognition systems, machine learning, and neural networks in academe, industry, government, and the popular imagination. The New York Times recently called today's moment, quote, the Great A.I. awakening. Yet this view, and many of us, fail to attend to AI's previous awakenings. In 1985, Alan Newell, this association's first president, wrote, quote, there is no doubt, as far as I am concerned, that the development of expert systems is the major advance in the field during the last decade. The emergence of expert systems has transformed the enterprise of AI. So today, we'll attempt to open up this history, its transformational aspects, and its connections to today's AI awakening by hearing from each of our panelists about their experience of this history and a closing joint discussion. So Ed, could you discuss your work in the first decade of artificial intelligence research and your own intellectual interests that led to the emergence of expert systems in the 1960s?
Let me go back to the first generation. The AI field began with a set of ideas like a big bang about the nature of human thought and how to model it by computer. And the ideas came from some truly remarkable individuals. Their ideas about problem solving, recognition, and learning were fundamental, but few. There was a focus on deductive reasoning processes, logic-based or based on heuristic search, and on the generality of these reasoning processes. In 1962, I wrote about the need to move beyond deductive tasks to the study of inductive processes and tasks which I viewed as dominant in human thought. But it took me 2 years until 1964 to frame this pursuit in a way that I thought would be fruitful. Being an empirical scientist, I was looking for some people to observe with the idea of modeling their behavior. Now, why did I choose to model the thinking of scientists? Because I saw them as being skilled professional induction specialists, constructing hypotheses from data, and I thought they would be reflectively curious and reductionistic to enjoy allowing others like me to explore their thought processes.
Could you tell us, Ed, about some of the scientific experts with whom you worked?
In 1964, I was fortunate to find an enthusiastic collaborator, Joshua Lederberg, professor of genetics and Nobel Prize winner at Stanford. He too was interested in the question, can AI model scientific thinking? So our work together began in 1965 after I joined Stanford. As an aside, Lederberg's mind was one of great vision and insight, one of the top minds of the 20th century in my view. But Lederberg was the gift that kept giving. In 1966, Lederberg recruited for us Professor Carl Djerassi, one of the most influential chemists of all time, the father of the pill and the head of Stanford's mass spectrometry laboratory. So,
Could you talk about, in your work with these scientific experts at Stanford, the development of your first testbed program for, exploring your ideas about induction and expertise?
yeah, so like I said, I'm an empirical scientist, not a theoretical one. I needed a test bed in which to do these AI experiments. And Lederberg suggested the problem that he was working on, the inferring hypotheses about organic molecular structures from the data taken by an instrument called a mass spectrometer. Lederberg was doing research for NASA on the design of a Mars probe, designing a mass spectrometer system for detecting life precursor molecules such as amino acids. In this experimental setting, the testbed, we could measure month by month how well our program, which was called heuristic dendrol, or later just dendrol for short, was performing compared with the performance of Djerassi's PhD students and postdocs on the same problem.
Well, after several years of effort, as we get to 1968, could you describe the kind of fundamental lesson that you had learned from this work?
So we proceeded experiment by experiment in this test bed. One of the great experimenters of all time is sitting right next to me here. Moving toward higher levels of performance in mass spectral analysis that propelled the movement to higher levels of behavior. And that was, what did that was the knowledge that we were systematically extracting from the experts in Djerassi's lab. Most of this knowledge was specific to mass spectrometry, much heuristic knowledge, but some was general chemistry, chemical knowledge. So in 1968, I was writing a paper with Bruce and Josh Lederberg in which we chose to summarize the evidence from the many dendrol experiments from mid-65 to mid-68. It was evident that the improvement in dendrol's performance as a mass spectrum analyst was almost totally a function of the amount and quality of the knowledge that we had obtained from Djerassi's experts, and that it was only weakly related to any improvements that the AI scientists, like me and him, had made to the reasoning processes used in dendrol's hypothesis formation. So in 1968, I called this observation the knowledge is power hypothesis, one data point. Later, as the evidence accumulated from dozens of or hundreds of expert systems, I changed the word hypothesis to principle. And the title of the 1968 paper was specifically worded to contrast what we called the dendrol case study with the main paradigm of the first generation of AI that focused on the generality of problem solving. Those of you who are old enough in the audience remember GPS. This was a major paradigm shift for AI research, but it took more than 5 years for the new paradigm to take hold and produce the quote that, the evidence that Newell was responding to in that quote that David gave you. So I think that's the end of that story.
Would you say that, well, is it your belief that this phrase, "in the knowledge lies the power," holds true today when thinking about
Yeah.
AI?
The knowledge is, yes. The knowledge is power principle is observed in almost all AI applications. For example, in the large number of advisory apps, hundreds that range widely. For example, these are just from the last 2 weeks of the New York Times and the San Francisco Chronicle and Wired magazine. Divorce law, consumer health advice, planning of travel vacations, income tax advisor and assistant. There was a time that the income tax advisor expert system was the biggest selling expert system of all time. Also, in every one of the justifiably popular AI assistant systems, such as Siri and Alexa, specifically, people now use the word skills to count the specific expert knowledge bases, large or small, that each assistant has. Alexa is said to have many because it is an open system. Siri has far fewer skills. In machine learning R&D, correctly dimensionalizing the feature space is important. And machine learning engineers use knowledge from experts in making their design choices. That is what we call now feature engineering. In some critical applications, for example, like car driving, machine learning's recognition processes can handle most of the cognitive load, but not all. Sometimes, for the so-called edge cases, higher level knowledge of the world will need to be deployed.
Well, perhaps we could pause for comment or observations from the other panelists at this point. I would particularly be interested in other people's reactions when they first encountered the knowledge principle or hypothesis, whichever it was, happened to be at the time. Does anybody have a comment?
We'll get to it.
Okay. Well, then perhaps, well, thanks very much, Ed. Perhaps then we'll move on to Bruce. Bruce, could you discuss how the representation of knowledge and knowledge engineering more broadly developed through the mid-1970s?
Well, we didn't use the term knowledge engineering until the 1970s, but we did talk in a 1969 paper that Ed and I were co-authors of with Georgia Sutherland about knowledge elicitation in AI. It was at a machine intelligence workshop, and people there were somewhat stunned that we were talking about organic chemistry. You remember that? And John McCarthy rescued me during a talk by saying to somebody who was giving me a hard time, "Sit down, be quiet, you might learn something." I forever after loved that man. Well, there were other groups working on knowledge representation at the same time. Harry Popel and Jack Myers at Pitt were working with an emphasis on ontologies and mechanisms. Peter Zolovitz was working with Dr. Bill Schwartz, and that led to a lot of work on the object-oriented frames paradigm. Kaz Kulikowski was working on knowledge engineering with Dr. Aaron Safir at Rutgers. There was work in Europe. The LV project came later. There was a lot of isolated work in France, replicating some of the early expert systems work, and several projects in France from commercial firms, Schlumberger and Alpha Aquitaine being two of the most important. The Japanese Institute, what they call it, Institute for New Generation Technology, ICOT, was working on fifth generation computing, largely from a point of view of logic and using, the French were using Prolog, and so did the Japanese. So I think our lesson there was that the important part was encoding knowledge. The language you used, Prolog or Lisp or something else, didn't matter nearly so much as the paradigm of starting with an expert's knowledge. But we also saw in that time that knowledge engineering could focus on the objects and their relationships in an ontology, a hierarchy. They could focus on the inferential mechanisms that were going on. And in Dendral, we were very much interested in what we called the situation action rules at the time. There was an action in the right-hand side of the rule, not just a Prolog kind of logical assertion. So, yeah.
Well, I was, as a former student of the subject myself, I was curious to know how your background in the philosophy of science, how did that factor into your contributions to this knowledge engineering area?
I didn't know that about you. I'm glad to know that. Well, I was fascinated with the reasoning process, as I'm sure you were. My dissertation was on the process of discovery and trying to orient it into a framework where, in the middle of my dissertation, I got to know this man in 1963 and began reading the early AI work, mostly by Newell and Simon, the Rand Corporation publications there. And it convinced me that we could make a logic of discovery out of the paradigm of search and a constrained search. So that was the focus within which I got to know Ed and came into this field. So when Ed offered the opportunity to work on Dendral, it was just a godsend, because here was an opportunity, one of the early experiments in computational philosophy, to try to do philosophy but with an empirical bent, namely writing programs that would actually produce something that was testable. Then I started these discussions with Carl Jurassi's postdoc, Alan Duffield, and his reasoning process about mass spectrometry and the interpretation of mass spectra was just exactly what I needed in order to instantiate some of those ideas about capturing knowledge about data interpretation and then subsequently theory formation. You've got to, I think, want to contrast this work with other work that was going on at the same time in which people were acting as their own experts. I could not by any means claim to be an expert in chemistry or certainly not mass spectrometry. And there were other people, though, like Joel Moses at MIT, who was an expert in symbolic mathematics, and Tony Hearns in symbolic algebra, Ken Colby in psychiatry, Todd Whipke in chemistry. These people were also doing knowledge elicitation, but it was in their own heads. So it was more like just introspection.
I was also curious to learn if you could describe what antecedents there were, if any, about representing the knowledge of a particular domain as rules.
There was a logician who published a paper, Emil Post, in 1943, using production rules as a complete logical system. That certainly has to be one of the precursors of our work on production systems. Although we weren't following it directly, it was certainly there. Art Samuel's work in The Checker Player, Art had interviewed experts to understand what is the feature vector, and then developed, he did a good deal of reading about checkers, but it was that expertise. And the influential part about that was that his machine learning component, that once you had the expertise in a first order form, it could be improved on automatically. That impressed me a great deal, and I always wanted to be able to do that. So we subsequently developed a learning program we called Metadendral that did learn the rules of mass spectrometry from empirical data. A footnote on that, the data were very sparse. It took about one graduate student 1 year to obtain and interpret one mass spectrum. So we couldn't ask for very much data. This was not a big data problem. And we substituted knowledge for data in that, and we continue to believe, I continue to believe, that that's a good trade-off when you don't have enough data for the big data kind of learning. So just three other things. John McCarthy's paper, Programs with Common Sense, made a very strong case that whatever knowledge a program was using, it had to be in a form that it could be changed from the outside. And that was something Art Samuel was doing with the feature vector weights, but something we were doing with the dendral rules of mass spectrometry that made a very big difference. Now, Bob Floyd and Alan Newell developed a production rule compiler at CMU, and that led to Don Waterman's work on representing the knowledge about poker play in a production system. And Don's work was extremely influential in giving us the sense that that was the way to do it. And finally, Georgia Sutherland had been working with Joshua Lederberg on knowledge elicitation and putting that knowledge into separate tables. They were not rules, they were constraints for the generator, but they were referenced in a way that they could be changed as data. Those were, in my mind, the most important precursors.
At the time and subsequently, what limits have you seen about in this manner of representation of knowledge as rule?
We saw a lot. And our friends at MIT and elsewhere were quick to point out others. We wanted to be testing the limits of a very simple production rule architecture, and we knew it was limited. We just didn't know quite where it would break and why. So that was the nature of many of the experiments that we subsequently published in the Meissen book. And I would encourage people to take a look. But let me quote from that. Our experience using eMeissen to build several expert systems has suggested some negative aspects to using such a simple representation for all of the knowledge. The associations that are encoded in rules are elemental and cannot be further examined except with some additional text that we put into some extra ad hoc slots. So continuing the quote, a reasoning program using only homogeneous rules with no internal distinctions among them thus fails to distinguish among several things: chance associations, statistical correlations, heuristics based on experience, causal associations, definitions, knowledge about structure, and taxonomic knowledge. All of those were things that we were failing to capture in the very simple, more or less flat organization.
Well, Bruce, could you briefly, if possible, describe the fundamental lesson that you took away from this era of knowledge engineering?
Can I do three? There are three different perspectives. From the point of view of computer science, I think the knowledge is power principle is the most important lesson, and it's one we certainly have said more than once. At the level of user acceptance, I think the main lesson is that a program needs to be able to explain its reasoning in any decision-making situation with high stakes. And third, at the implementation level, the main lesson is flexibility. And in the final chapter of the Meisen book, chapter 36, it took us a long time to get there, we wrote, if we were to try to summarize in one word why Meisen works as well as it does, the word would be flexibility. By that, we mean that the designer's choices about programming constructs and knowledge structures can be revised with ease, relative ease, and that the user's interactions with the system are not limited to a narrow range in a rigid form. So, knowledge, explanation, flexibility.
Thank you. Well, Randy, turning to you, could you tell us about what you saw as the most interesting developments in the field that emerged from, let's say, the mid-'70s to the mid-'80s?
Yeah, I think there were a number, let me get the microphone. I think there were a number of interesting things. One interesting lesson was the value in generalizing the work that had been done. Initially, of course, this was the generalization from the individual applications to the so-called expert system shells. They were put into fairly wide use. Lots of applications got built using them. Not all of these things were acknowledged as expert systems, and some of them, I think, weren't particularly true to the original inspiration and architecture. But the real point is they adopted and spread the ideas, two good ideas, namely that to be good, a program needed a reasonably large collection of task-specific knowledge, and second, that there were at least semi-principled ways to gather and represent that knowledge. These tools were in some ways analogous to the open sourcing of deep learning tools that are being distributed now. And like those tools, they provide a substantial boost to people who are trying to build these systems. But as always, it's best if you are one of the anointed ones who know how to use the tools. That's how you get the best use out of them. I think it was true then, and I think it's true now. Another interesting lesson was the way certain insights seemed to echo through the years. We kept seeing the value of explicit, readable representations of knowledge, using familiar symbols in knowledge representation, expressing knowledge separately from its intended use, which has, of course, already been mentioned. The most immediate consequence of these ideas is to enable multiple uses of the same knowledge. So we had systems that were doing diagnosis with a body of knowledge, explaining the reasoning and the result using that same body of knowledge, and then going ahead to teaching somebody with that same body of knowledge, all from a single representation. And just as when you're building a program, the virtues of encoding something once saves you from version skew, it was the same thing here in version skew in the knowledge. One of the nice examples of this multiple use of knowledge came out of the work of Bill Clancy, where the basic inspiration was if we can debrief experts and transfer their knowledge into the program, is it possible to get the program to transfer the same knowledge into the head of a student? That, in turn, led to lots of interesting work that has already been hinted at in understanding what was insufficient about Meisen's very simple rule-based representation. The systems got considerably more power when that knowledge, which was implicit in the rules, got explicitly captured and represented in some of the work that Bill Clancy did. Another outcome in that body of work and in other work on intelligent tutoring was the idea that explicit representations of knowledge permits a kind of mind reading, or at least mind inferring. If I have an explicit model of what someone needs to know to accomplish a task, and they make a mistake in doing that task, say diagnosis, I can plausibly ask myself, given my model of what they ought to know, what defect in that knowledge would have produced the error that they produced? It's an interesting form if not mind reading, at least mind inferring. The final lesson was the ubiquity of knowledge. Task-specific knowledge, of course, for example, medicine. Knowledge about debriefing, how do we get the knowledge out of the head of the expert into the program? Knowledge about tutoring, how do we transfer that into the students? And knowledge about the general task, diagnosis as a particular variety of inference. Everywhere we looked, there was more to know, more to understand, and more to write down in explicit forms.
Thank you. Could you also now discuss for us your involvement with and your views on the importance of issues of explanation and transparency in artificial intelligence.
Yeah, I've been interested in this stuff for several decades. The bad news, for me at least, is after all that time, this session is about 2 years too late for me to be hailed as visionary. Because the idea that AI programs ought to be explainable is now in wide circulation, alas. Where were you guys 40 years ago? There's a lot of interest, of course, in getting understandable AI. There's lots of experiments in getting deep learning systems to become more transparent. As many of you know, Dave Gunning's got a DARPA program on explainable AI. And the overall focus that's come about in looking at AI not as automation working alone, but having AI work together with people, all of these things are going to work better with systems that are explainable and transparent. So there's lots of reasons to want this. The most obvious ones are trust and training. Trust is obvious. If we've got autonomous cars or medical diagnosis programs, we want to know we can trust the result. But I think training is another issue. If the system makes a mistake, what ought we to do about it? Should we give it more examples? What kind of examples? Is there something it clearly doesn't know? What doesn't it know? How do we explain it to the system? So transparency helps with making the system smarter. One key issue, I think, is the representation and inference model. In what sense is the representation and inference model in our programs either similar to or a model of human reasoning? It seems to me that the closer the system's model of systems representations and model of reasoning is to human representations and reasoning, the easier it's going to be to bridge that gap and make them understandable. A kind of counterexample of this is currently the vision systems, the deep learning vision systems that are doing a marvelously impressive job of image labeling, for example. They're said to derive their own representations, and that's great, but it's also a problem because they're deriving their own representations. If you want to ask them why they thought a particular picture was of George Washington, what could they possibly say? Now, the issue is made a little bit better by, a little bit worse by the collection of papers these days that show that deep learning vision systems can be thrown off completely by some image perturbations that are virtually invisible to people but cause these systems to get the wrong answer with very high probability. Now, the problem is that we don't know what they're doing and why they're doing it. So when you show the system an image that looks to us like a flagpole and it says, that's a Labrador, I'm sure of it, if we ask them why you thought so, it's not clear what kind of answer they can give us. Now, there's been some work in this area, of course, and to the extent that these systems use representations that are human-derived, they're better off. There's some clever techniques being developed for examining local segments of the decision boundary. But even so, when you start to talk about local segments of a decision boundary in a multidimensional space and hyperplanes, I suspect most people's eyes are going to glass over. It's not my idea of an intuitive explanation. Now, this works in its very early stages, and I certainly hope that we can come up with much better ways to make these extraordinarily powerful and successful systems a whole lot more transparent. But I'm still fundamentally skeptical that views of a complex statistical process are going to do that. Which brings me to a claim that I will make and then probably get hung out to dry on, but I will claim that systems ought to have representations that are familiar, simple, and hierarchical, and inference methods that are intuitive to people. The best test, I think, is simple. Ask a doctor why they came up with a particular diagnosis and listen to the answer, and then ask one of our machine learning big data systems why they came up with that answer and see about the difference. So let me summarize. If AI is going to be an effective assistant partner, it's going to have to be able to be trained in focused ways, and it's going to have to be able to divulge its expertise in a way that makes sense to the user, not just to the machine learning specialist.
If I could just ask a follow-on question, in listening to you talk about the importance of both explanation and transparency, it made me wonder do you think there's a risk that making those requirements of a system might limit them in some way, cut off a potential that they might have?
I think there's no risk. It will happen. And I actually know this from experience. I have a paper in machine learning from last spring It has to do with a medical diagnosis program of sorts where we built the best possible classifier we could in a system that had about 1,000-dimensional space. Its AUC was above 0.9, and the humans who are doing this task have an AUC of about 0.75. It was great, except it was a black box. So then, working with Cynthia Rudin, who was then at MIT, we built machine learning models that were explicitly designed to be more transparent and simpler. And we measured that performance, and now it's down about 0.85. So not only do I know that explanation and transparency will cost you something, we're able to calibrate what it cost you in at least one circumstance. So I think there's no free lunch, but we need both of those things.
That's fascinating. Any comments or observations from our other panelists at this point?
Yeah, I'll make a few comments in a few minutes, but just on the transparency side, it's a really fabulous area for research, and I expect to see some continuing stream of innovation in that realm. This whole idea of what can you do with generalized additive models with what's called shaping functions to squeeze most of that area under the curve out for your classifiers, while having something that you might say is more explainable and understandable. But even so, there's this idea of what we long back for, to the Tricia system that would talk to you about the logical chain and read back kind of a script of what the reasoning was. It's quite different. But I think we can sort of still make progress as a high-level comment there.
David, I just wanted to
Yes,
add on to what Eric.
Sorry.
Just want to add on to what Eric just said, and I'll change the words a little bit, Eric. But I've been engaged in giving extended tutorial to a group of lawyers at the very, very top of the food chain in law. The message is, we need a story. That's how we decide things. And we understand about those networks, and we understand about, at the bottom, you pass up 0.825, and then it changes into 0.634, and then it changes into 0.345. That's not a story. We need a story, or we can't assess liability, we can't make judgments. We need that explanation in human terms.
Yeah.
David, do we have time for one more?
Absolutely.
A footnote on what Randy mentioned, Bill Clancy's dissertation, and I made Bill just a little bit angry by calling it one of the great experiments with a negative outcome. The hypothesis there was that production rules would indeed be adequate for teaching, and that was just plain false. And Bill showed not only that it was false, but what to do about it then. But I would encourage people to think about the negative conclusions as well as the positive ones.
And do we have time for one more comment on that? Going back to what Ed and some other folks were saying about the inadequacies of rule-based systems, absolutely true, and Bruce's list is an excellent one. I don't want to overlook the virtues of trying very hard with a simple representation, because I think there was virtue to it. It forced us to think very carefully about what the knowledge was. And the taste issue is how long you keep pressing on that because it reveals things, and when does it turn into a Procrustean bed? And making that decision point is one of the key things about doing the research properly. Ride it for as long as you can because it helps you see things simply, and then throw it away when you realize exactly why it's holding you back. That's the hard judgment call.
Thanks. Eric, perhaps we can now turn to you, and would you tell us about your work to incorporate Bayesian inference into expert systems?
Well, let me speak more generally as a representative of a rising group of young folks and some mid-career and older folks that represent what might be called a probabilistic revolution that occurred right at the time that a period of time people labeled as AI winter. This was a time of kindling and embers and sparks into a full firestorm, I think. And so that's how I view what's called, AI winter. But I came to Stanford University very, very excited about principles, structures, architectures of cognition, and very excited about what was being done in the labs working on expert systems of the day in the early 80s, really applying theorem-proving like technologies to real-world tasks, helping people in areas like medicine. I remember talking to John McCarthy very early on, liked what he was doing in Common Sense and his representations, and I started talking about medicine and healthcare and these expert systems folks, and he very quietly in his office just put his finger up and said, "Go see Bruce Buchanan." And so I went to see Bruce and spoke to Bruce and met Ed and Ted Shortliff and others. And we were very excited about the idea of really going beyond toy illustrations and building real systems that can really augment people's abilities. The complexity of healthcare, which I got very interested in, let us look carefully at the Mycin system, which was one of the, primordial systems that led to some thinking about architecture and essential notions of E-mycin and what that meant and so on. And we realized that folks like Ted wrestling with the complexity of the real world, really trying to deliver healthcare decision support, we're introducing these numbers, numerical information on top of the logic theorem provers, or the chainers, the production systems, called certainty factors. And I joined up with David Heckerman, and we started thinking about, wow, I wonder what's going on. How does this relate to the probabilistic reasoning and the probability we learned, that we knew and loved from the past? By working things through, it seemed that there was certain assumptions being made in these systems that were actually consistent with probability theory, but when you laid it out, showed that these were the push for logic and the push for the chaining of chunks of human knowledge led to assumptions that we would call modularity. So we could actually go back and then say, well, we can write down what this means from the point of view of probability theory. And what we saw was a very beautiful framework that had been actually discovered earlier and written about by Carnap in the Foundations of Scientific Confirmation Theory, about how you can sort of have modular independent updates and pass them through chains of reasoning. But that was only one possibility, and we started trying to open things up, trying to relax some of the independence assumptions on probabilistic distributions that these systems would imply if you worked it all out. And we then were faced with this, trying to generalize this with the full raw power of probability, but the full intractability at the same time. And this led us to really start reasoning about, from the point of view of the same departments that had done interesting work on abstraction, into the prospect of backing off full probability distributions, which were clearly intractable, coming up with new methods, models, languages of abstraction that might give us some expressiveness while reducing the need for so many numbers and the need for so much computation. I should say, during this process, it wasn't easy working with our mentors at the time. I'm not going to say who exactly it was, but we were. Someone claimed that we had physics envy by going to numbers, and these numerical methods they had already been cast aside by AI when AI branched away from cybernetics and operations research and management science, and those kind of were boring fields. They didn't really get cognition. They weren't working at the levels of symbolic reasoning. And why would you ever do a throwback like that? Even talking to a person I view as a distant but close mentor, Herb Simon, I remember talking and getting excited about probabilistic reasoning under bounded resources. Wasn't this bounded rationality? And hearing some long pauses, and then, are you saying you're a Bayesian? And saying, okay, well, I yes. And to sort of, we stayed good friends and so on, but even with my proclamation about what I was doing. But we did find some rich support in other departments. Patrick Suppies with his work in measure theory and probability. Ron Howard who became my main advisor with his work on Markov decision processes, George Danzig, who all were very interested in what was going on in the expert systems world and felt left out that their methods hadn't been employed more. We also ran into other like-minded souls in the same generation. I see Ben Grossoff sitting right here in the front of the room, Mike Wellman, Moises Goldschmidt, Craig Boutelier, who's at the meeting, later Daphne Kohler, Nir Friedman, Adnan Darwich. There was a rising invisible college across campuses and people interested in, let's figure out how we can get to the same power and the same kinds of abstractions that we celebrated earlier in the 60s and 70s in these systems that we were building to help people do reasoning. And I have to say, this area led to some really interesting work, but I want to point out that it was the expert systems tradition and aesthetics and goals that really framed the initial probabilistic expert systems, or Bayesian systems. For example, we really thought about what was knowledge acquisition. How could you do it with tools that would ease the effort, raise levels of abstraction? The whole tradition of knowledge engineering in defining distinctions and what became features and relationships. The whole notion that we were helping people to become better. We could never imagine, here we are in 2017, and we have folks saying, we have a new idea. We're going to augment human reasoning. Or we have a better idea, human-aware computation that will make people better. Well, the whole expert systems tradition, this was considered not even stated. It was implicit. It was base. The fact that we would be helping people work in a situated manner on tasks at hand, the patient here, the chemical spectra coming out of the system. And so these notions, I think, unfortunately, have faded with time. Even though we have powerful tools now, we're only getting back to how do you deploy them in ways that really are made and designed to help people on complex tasks in real time. Let me stop there.
Can I comment briefly on something Eric,
Sure.
Eric said? I just wanted on record, I think we're being taped and videotaped here, but I want to acknowledge that he used the word primordial in referring to some of the early work. This is just his disguised way of referring to this side of the table as dinosaurs, and I want that acknowledged. You may continue.
Thank you. Duly noted. Well, Eric, could you continue and talk about how this probabilistic turn changed the development of expert systems per se, especially in the areas of biology and medicine?
Well, I should say that the first systems we built, like Pathfinder, actually, again, back to the early notions, had notions of explanation. We really tried to make explanation work. Why was a question being selected, showing the cost and benefits of answering a question, showing the value of information by breaking it down into components. So we had explanation running. We showed how we could even change that to text explanations at the time. We rapidly realized we had a challenge with the opacity of the reasoning itself at times. And so one of the early things we did was we actually came up with what we called a coherent strategy for putting an abstraction, an ontology into the system that would impose human-like reasoning and slow down the inference. So, for example, a pathology system would say, let me use the full power of probability and decision theory to do benign versus malignant first. When I rule out benign, I will then pop open the ontology and then work on the next subproblem, but do it in a human-oriented way. And pathologists really liked that. So we had the sense that we could overlay human-like constraints and transparency by slowing down the system a bit. You still get to the right answer. So those notions, again, were consistent with the earlier intent. And we saw an explosion of these kinds of systems in the marketplace. We actually we saw commercialization and a fielding of tools and shells using probabilistic reasoning methods. But the real change, I think, in the field happened when it became feasible to store data and to capture data. Remember, back in those first days of the probabilistic systems, we still didn't have much data. We still had to design systems that could capture conditional probabilities from experts in the same way you capture rules from experts, laying out the networks and then asking experts hundreds of numbers and coming up with tools and ways of doing that. That was very similar to knowledge acquisition at first. But with more and more data coming available and with machine learning procedures that initially we used to mix machine learning and human numbers, and later just started focusing on the data itself, we ended up seeing new kinds of systems being built. And let me just say that things have moved away from this idea of reasoning deeply about tasks and tracking a task as it unfolds, and more in terms of one-shot classification, myopic pattern recognition in a quick cycle, recommender engines that do one-shot inferences, search engines that use machine learning, one-shot rank lists. And there's a huge opportunity ahead to basically, I want to just highlight this, to harken back to the kinds of problems and the kinds of experiences we were trying to generate in the expert systems days with modern tools. And I think that that's going to be a very big open area for us to innovate in.
Thank you. Yes, Bruce.
Eric, you were the one who introduced me to Ron Howard's notion of influence diagrams. And that is such a simple and powerful tool for knowledge elicitation, knowledge engineering. You want to say just a word about influence diagram?
So so the whole family we call graphical models is very expressive notation, symbolic system for basically talking about, in a compact way, probability distributions and highlighting critical independencies in the world that make our systems tractable and that capture what it is we learn when we learn about the world in a way that we can make decisions and inferences. Influence diagrams extended this graphical modeling of distinctions and their probabilistic relationships to action in a rich way by introducing representations of utility and actually decisions or actions in the world. And once you did that, you had a beautiful way of just understanding a sense for both probabilistic and causal associations, as well as a whole bunch of stuff that falls out beautifully for free in some ways, like, for example, the ability to reason at any moment about what's the most valuable information to collect next that you don't know about yet or that you want to refine. And that could apply to computation itself. What's the next best thing I should think about as a system? Getting into notions of bounded rationality and implying and framing work in new kinds of cognitive architectures that would make use of probabilistic reasoning and decision theory. But the beauty that Bruce was talking about is the ability to lay out in a graphical, visual way that experts, that human beings, and non-experts can understand, and even play with in a tool where you can just draw arcs, introduce new distinctions, and understand and propagate uncertainty in a way to compute best actions, most valuable information to collect next. And those kinds of basic functions can start to play a basic role in doing things that the expert systems of the 60s and 70s were doing.
Well, to my horror, our panel is drawn. Oh, please, Randy.
I want to make one more comment. I've always preferred the term knowledge-based system as opposed to expert system, and I like it because it advertises the technical grounds on which the system works, large bodies of knowledge. And I think it's interesting because it holds for people as well as programs. It gets to an answer to the question, why are experts experts? Do they think differently than the rest of us? Do they think faster than the rest of us? The claim that people and programs can be experts because they know a lot And there's evidence of this in the early work of Chase and Simon, who talk about, I think it was 30,000 patterns to be a good chess player. More recent work that says you need to spend 10,000 hours of experience on something to learn to be good at it. There's lots of evidence that knowing a lot is the basis for expertise. And I think that's interesting. It has a not frequently commented on sociological implication. I think it's a profoundly optimistic and inclusive message. To the extent that expertise is in fact knowledge-based, it becomes accessible to anyone willing to accumulate the relevant knowledge. That's a crucial enabling message, in my opinion, perhaps the most important one in education. Yes, you can learn to do this.
Well, thank you, Randy. I was just going to turn to a suggestion that Ed had when we were talking about organizing this panel to close with asking each of you to present to this audience, a single sort of takeaway message. I think we may have heard Randy's, and I was just...
Sorry, got out of order.
No, and I just thought perhaps this might be a good time to turn to the takeaway.
Okay. I just wanted to make one observation before my takeaway, though, which is why I grabbed the mic. David had asked us in advance, one of the questions was, to what extent were we motivated by getting behavior that was simply the best in the world, the best there is? And I would say that we were significantly motivated, although it was unstated pretty much around, but we were really after a dendral that could exceed the capabilities of mass spectrometrists. And in fact, Carl Djerassi did a little experiment with mass spectrometrists around the country. And the Meissen group did an experiment with experts in blood infections around the country, which showed the capability of Meissen very good compared to those specialists. I worked on a defense application for DARPA, spent a few years on it, and then DARPA led a contract with MITRE to assess the capability of that system versus the humans who were doing the work in the Defense Department. And the system was significantly better than those humans. As early as 1957, Herb Simon, you probably don't even know, you young people don't even know who Herb Simon was. One of the
guy who
greats of
called
the
me a
20th century.
Bayesian.
But he made the prediction that a machine would be world chess champion in 10 years. Well, he was wrong about the time, but he was right about becoming world chess champion. So I think we were significantly motivated at least I was significantly motivated by doing that. Anyway, what's my takeaway message? It could be an easy one, and I'm going to dismiss the easy one. The easy one is, of course, is that in the knowledge lies the power. If you take on a job, ask yourself first, where am I going to get the knowledge to do that? This keeps getting referred to on panel after panel, talk after talk as domain-specific knowledge. Yes, domain-specific knowledge. But what I really want to say is something that Peter Friedland, who's sitting up in the front here, reminded one of our former students who worked on a molecular genetics program called MalGen that I won't give you the history of it, but he was pointing out the multidisciplinarity of the work that was going on in the laboratory. In fact, Eric is a beautiful example of that. He's an MD PhD, and we had several MD PhDs that were among the best students we ever saw, were MD PhDs, and people interested in a wide variety of fields. Everyone was deeply involved with the details of somebody else's business. And that's really exciting, to have a license to do that. So I would say, for the young people in the audience, get involved with other disciplines.
Thank you. Bruce, do you have?
Well, it's a hard question, but from the point of view of philosophy of science, one of the strong lessons, and it was confirmed by one of the great dissertations in AI, namely Randy Davis's dissertation on meta-level reasoning, namely the strategies that scientists and other problem solvers use can be written as knowledge-based systems. The strategy itself is knowledge, but it's one level above the domain knowledge. So I take that as one of the very strong lessons to come out of 2 decades of expert systems work.
Thank you. Eric?
Yeah, I would just suggest that people today look back at the history, look at the systems that were built, look at the fanfare of the mid-'80s and the collapse of that fanfare, the rise of the probabilistic methods, but look at basically the goals and the kinds of systems that were being built. Even some of the architectures, the Blackboard models, for example, not just the production systems, but Blackboard models were really the first multi-layer models that even had semblances of backprop running in them, if you look at them carefully. The notions of explanation being critical, transparency, meta-reasoning, the idea of systems that have dialogue and that track with users, that are embedded and situated in a task in the real world and that augment human cognition. These are all key themes that were so basic we didn't even talk about them in those days. And now they're coming back as questions, should we be doing more of this or that?
Well, won't you all join me in thanking our panel?